Okay, so we will end the chapter here and go to chapter 7. Okay, so at chapter 7, now as you can see, we're dealing with different forms of the signal. We have deterministic signal and then random signal and then unknown parameters. And now we come to the deterministic signal with unknown parameter. So as along the way, as you can see that we have different forms of the signal, and uh, we need to be well aware of the settings of the problem. Either either it be either it be just parameter, or it be deterministic signal, or it's a random process, or it's a deterministic signal with unknown parameter. And sometimes we have prior information, sometimes we don't, and so you deal with different situations by different approaches. Okay, so in this chapter, a problem of great practical importance is the detection of signals that are not completely known. The lack of signal knowledge may be due to uncertain propagation effect, as in mobile radio, or to unknown signal generation mechanisms responsible for stock market trends, for example. Being able to design effective detectors requires the advanced theory of composite hypothesis testing that was described in chapter 6. In this uh, succeeding chapters, we apply the theory to many detection problems. So uh, we will deal with the detection of deterministic signals with unknown parameters. Okay, so I think the best way to demonstrate this is to go directly uh, to the examples. So now we are at page 253. So we now consider the problem of detecting a deterministic signal known except for amplitude in white Gaussian noise. So we have a H0 that is again noise only, or we have H1, and that H1 has a signal with an unknown amplitude A, okay, and plus a noise. The S is known, but the amplitude SA, the amplitude A is unknown, and Wn is white Gaussian with variance sigma square. So this problem is exactly of the form described in chapter 6. If S is equal to 1, then the whole thing becomes unknown DC level, right? But here it's no longer a DC level, it's a signal S. There it was shown that if the sign of A is known, then the UMP test exists. We did that, right? We did that in chapter 6. If the sign is not known, then the UMP does not exist. And then we must either employ a GLRT or Bayesian approach. Okay, so if the test statistic and its ratio can be found without knowledge of A, then the test is UMP. The LRT, here comes the important part. The likelihood ratio test will decide H1 if this likelihood ratio is larger than gamma, or which we will just write it out. This thing becomes this thing, and then this thing has a mean, its mean is as, right? As the mean of the whole random variable. And then it has a multiplied by s as the mean. And take the logarithms and simplify. Then we get this, again, this cancels out and the exponent disappear, and then remaining power simplifies. You simplify it. You do some reformulations. Then we get this, and we further simplify a little bit, we get something like this. So now you have, this is familiar to us, right? It's like a correlation. Before we did that, and then it's multiplied by a, and we have a summation of x s is larger than this sigma square ln plus a squared over 2 summation s squared n equal to gamma prime, right? Then again, we need to know the sign of a. If a is larger than 0, then it's good because we can just cancel this out. We will divide this by a, then everything will be cancelled out. If a is larger than 0, then the NP test is to decide h1 if summation of this is larger than this, right? Because this whole thing is assumed to be a parameter gamma prime is divided by a. You don't change your sign because a is larger than 0. Or if a is smaller than 0, then we will decide h1 if this, because when you decide, no, I'm sorry, you divide something by a minus number, negative number, the sign changes. It's larger, from larger than to smaller than. So the summation of this whole thing is smaller than this, so we'll decide h1. So it changes the sign. In either case, the test is a UMP, uniformly most powerful detector, and reduces to the usual correlator structure. Remember that we say correlation. It becomes a correlator structure. If, however, the sign of A is unknown, we cannot construct a unique test. For example, if we assume this and use this, then poor result will be expected if A is actually negative. Okay, so this is to say that if we don't know the sign of A, then it's hard for us to use either this one or this one. So we need to know the sign. So the sign is a very important information here, right? Okay, so if A is larger than 0, then expect of this thing is equal to this. And this is the signal square summation. Of course, this is positive, but this is negative, then it's smaller than 0. Okay. So if a UMP test does not exist, so that the test statistic and threshold do not depend on the value of A, the performance of the detector will depend on the magnitude of A. The performance of the UMP test for either A larger than 0 or A smaller than 0 is easily shown to be something like this, where B squared is something like that, and we proved that before. But the point is, the UMP test exists if you know the sign of A. If you don't, then you come up with something like this, then you could get a very terrible result. Okay, but uh, it really depends on the prior information, whether you know A positive or A negative. If you don't, it could be negative and you assume it to be positive, then you get terrible outcome. Or it's positive and you assume it to be negative, you get terrible outcome. Okay, so and the next thing is generalized likelihood ratio test, GLRT. The GLRT will decide H1 if this is larger than gamma. Then A hat is the MLE of A under H1. So the A is the MLE, the A hat is the MLE of A, but the MLE is something like this, and as again, this is this is a mathematical estimation. It has to be done in volume 1 of the textbook. Okay, but we just assume that we know this, so we can plug this in, and then from 7.8, we know that we'll be able to show that the likelihood ratio can be simplified to this 7.8. Let's see, let me see. 7.8 here, right? It simplifies from likelihood ratio, but the A is replaced by A hat. Okay, so now we have this A hat comes in, and then larger than gamma prime, but A hat is like this. This is observation, this is a signal. And using some simplifications, you do this simplifies this, and finally we will decide H1 if A hat square is larger than this. But A hat square is larger than this. The whole description seems strange, right? Would you wonder where is the data? The data seems to disappear from the description, but don't worry about it. Let's come back and look at it again. The data is hidden in the A hat. So in other words, A hat is a function of the data. And now the data calculates A hat. Then this is like A hat serves as a proxy of the data. It's a proxy for the data. So A hat square is larger than this, and all those things are known, right? This is to be set, and this is known a priori. So equivalently, if we take A has absolute value larger than this, then we will decide H1. That's sort of the GLRT detector. GLRT detector. For noise only, we will expect A hat to be approaching to 0. And when the signal is present, A hat should depart from 0. It is therefore not unreasonable that the detector is based on the magnitude of the amplitude estimate. Alternatively, we have from this equation that we can actually calculate this T of x equal to summation of x. This is a correlator square equal to this, or equivalently, this is equal to that. And in fact, if you come back to take a look, you do have a correlator here, right, at the numerator. So it doesn't matter, it's equivalent. So the signal is just a correlator that accounts for the unknown sign of A by taking the absolute value. Then the detector of this form can be shown here. So this block diagram implements this whole thing. You have x comes in, you multiply with s, which is something like this, and you do the summation, then you get something like that. And you do the square, you do this square here, and you come up with T of x, and you compare with the threshold, and it gives you H1 or it gives you H0. So that's the GLRT. That's the GLRT for unknown amplitude. So the lack of amplitude knowledge will degrade the detection performance, but only slightly so from that of the correlator. Slightly so from, that means it's slightly degrading. So slightly degrading from the correlator to determine the detection performance. We first know that U of x, this is Gaussian distribution with this under H0, with this under H1. So PFA, you calculate it. I'm not going to repeat the details. condition on H0, you make a decision on H1, so on and so forth, and then you come up with this Q function. And similarly, PD you calculate, and then you come up with something like this. So eventually, PD gives you this outcome. And then we can plot PFA is if it's given, then you get PD versus this. So that's the detection performance for GRT. Then the next thing is the Bayesian approach. We now assume that A is a random variable again. This is a very special assumption because when you assume it to be a random variable, you need to have some prior knowledge. So now we assume that A is a random variable. It's a PDF n of mu A sigma A squared, and A is independent of this. So with these assumptions, we have under H1 that X is XA plus W. S is taking time samples. So this is just a Bayesian linear model with H equal to S and theta equal to A. From the results of section 5.6, we know that the NP tested to decide H1 if T prime or X is something like this. But it has to recall 5.6 and then larger than gamma pi. So here we have H equal to S, theta equal to A, mu sigma, mu theta equal to mu A, so on and so forth. So that we simplify it a little bit, we have test statistics, something like this. So notice that this is the outcome. And what do we have here? We have data observations, which is reasonable. And we have prior knowledge data, no, I'm sorry, sigma A squared. And then we have known information S here, S transpose, sigma squared, and then mu A. So everything is known, and then there's observation coming in. So everything is then reasonable. So we have test statistic, this plus this, right? Sigma A, S, sigma A, S, sigma, then X. So everything is known. So this is then the test statistic. Then of course with we go with some identity 恒等式, so we simplified it further. So we eventually get something like this, NP test statistic, which is a combination of a correlator. Right? Where is the correlator? Here. And the square correlator. So it's not, I'm sorry, this is the correlator. This is the square of the correlator. So it's not surprising to see this because the correlation structure often comes up in the likelihood ratio formulations. So it's not a surprise that we see things like that. So I think that's let me see. If sigma A is 0, what does it mean? It means that A has no variance. Then we have a simplified test statistic, which is the non-amplitude case, right? Because that's reasonable because mu A is equal to A if sigma A is 0. If sigma A squared approaches infinity, we have T prime or X equal to this, which is the Bayesian detector with no prior amplitude knowledge, right? So in order to implement the Bayesian detector, we require knowledge of mu A and sigma A. When this information is available, the resultant detector is optimal in the Neyman-Pearson sense. So that's the highest PD for a given PFA. Okay, I think 7.4 is the end of our discussion, and that will be the end of this of today's class, and our midterm exam will also covers up to here. And for those parts that are skipped, they are not included in the midterm exam. Okay, so thank you for your listening.